You're welcome to Maths 306, and we continue with the topic Group Actions and Syllogism Theorem. We actually now in chapter 2, the very first part. On the screen are the various topics we will be considering in the course of the video. Okay, so we begin with definitions. I always like starting with definitions. So once the definitions are in place, it's easier to understand what the terms and other applications that we might be needing or we would be using them for. So the first definition is what we call a group action. So we have a group action, and it is the action of a group G on a set Holmes. So you could change the notation to whichever notation we want. It could be G acting on a set X. Okay, so in our case, it's acting on a set Holmes. So when it does act on this set, we say we have it's a function actually, a function mu that acts on the direct product of the set with G and takes it back to the set Holmes. Okay. We had defined direct product in our last class, if you recall. So now this map is called an action if it maps, the map mu maps from the direct product of Holmes cross G and brings it back to the set Holmes, meaning that we have a map of this form. Remember, direct products, definitely there will be two elements, a tuple, right, or two tuple, and the map is mu. Okay, and we denote such an operation by the element alpha raised to power G, as you can see there. And once we have this map, first you must define this map. It must satisfy two conditions, the one associativity and the other identity. So associativity, if you take alpha raised to power G and in the bracket all raised to power H, it will be same as taking alpha raised to power GH. And the identity, alpha raised to power 1, will be same as alpha. Okay, and this will hold for all alpha in the set Holmes and for any GH in G. That's why it is all. Any element you pick in G must satisfy this condition. When these conditions are satisfied, we say we have a group action. The next thing you need to know is that we call this function a homomorphism. If you remember, we defined a homomorphism, right? So the homomorphism rho mapping from the group G into the symmetric group of order n, where the set is the set of the set Holmes, which we had used in the definition of the action, defined by this map. So you know the map is a function from G to the symmetric groups on Holmes, and this is how it picks its element. It will take G from the small letter G from the group G, and it will act by permutation of rho G. Okay, how does it look like? It will look this way. Okay, it take the G and the map looks like this. So what happens is that because the permutation is in the set of Holmes, right? Symmetric group, so it's going to take it as alpha rho G and it will give you alpha raised to power G, and this is called the permutation representation of G. So once you have a map of this form satisfying these conditions, we say it is called the permutation representation of G, meaning that G is extended to a permutation, right? So that's how you represent the set group the group G as a permutation. Okay. The next thing you need to know is the definition of the kernel of an action of G on the set Holmes. Now you know what a group action is. It's up here, right? You now know what a permutation representation is. The next you need to know is what we call the kernel of the action of G on the set Holmes. You know what a kernel is. We had defined it in the last class. The kernel is simply the map, a homomorphism that takes every element in the group G to the identity, right? The element that is collected is called a kernel. Those elements that are taken to 1. Okay, so we let G be as defined a group action, which we already know, and we call the kernel of this group action is defined as what you can see on the screen here. Now we know that the group action alpha G, right, is the notation on it, right? So every time this group action gives you back the same value of alpha G is taken, when G acts on the alpha, it gives you back alpha. We say we have an element, it collects that G, right? Because the G is acting, and G takes alpha to alpha. If that happens, then we put it in the set K, where K is our kernel. Okay, in extension, if we now use the homomorphism which we had defined earlier here, which is the permutation representation, it will look, as you can see on the screen, okay, to look like this. Now, the permutation representation rule is said to be faithful whenever the kernel is equal to 1. G is said to be faithfully, to act faithfully on the set Holmes. So now we have definitions in place. 1, we have defined a group action. 2, we have defined the permutation representation. 3, we've defined the kernel, right? And we have also defined what we call a faithful action, or an action when G acts faithfully on the set Holmes. That is, the kernel will always be the identity. We know what the kernel looks like. It's when G acts on the set Holmes. And so it picks its element. If G picks an element alpha and gives you back alpha. Okay, so that is what we call the kernel. That's an element, the kernel. And if we're using the homomorphism, which has to do with the permutation representation, it will look like so, like you have here. That's a definition. Okay, next. Now, the action G on the set Holmes is said to be trivial. Now, we know when it is faithful, it's a faithful action, right? To act faithfully. That's when the kernel is always equal to the identity 1, right? Now, we said it is trivial if alpha G is equal to alpha. So alpha raised by G equals to alpha for all alpha in the set. Okay, so it would be said to be trivial. In this case, the kernel, we're not using the homomorphism here, right? We're not using the homomorphism of phi, okay? Now, we said it is trivial when alpha G is equal to alpha. Now, the action of G on itself by the rule, this rule you see here. So whenever it takes G acts on X and it becomes XG, so that is to say the action is called a regular representation. Okay, so whenever this happens, so if it was alpha now, if it was alpha equals to, sorry, let me write it. So if alpha G is equal to alpha, we say we have a trivial action, right? Now, if it is alpha G and it goes to give you alpha with G by the side, we call it a regular representation. Okay, so those are two definitions again added to the collection of definitions you ought and need to know. Now, let G act on the set Holmes. You know what a group action is already. It's a mapping satisfying two identities, associativity and identity, right? So if G acts on the set Holmes, if we pick alpha in the set, we define the stabilizer. Now, what is a stabilizer? A stabilizer is a subgroup of G that contains all elements that fix alpha. So like when you see in the case of the trivial action here, so if all the time G picks any element, even if it picks Y, G acts on Y, and it gives you back Y. Every time it does that, the stabilizer will be the set collecting all the elements that whenever G acts on it, it will always fix it, leaves it the same. Okay, so let G act on the set Holmes. If we pick alpha in Holmes, we define the stabilizer of alpha by G with the subscript alpha to be equal to this set here. So it collects all the G's that will always fix the alpha. So any G, so imagine a set, say G, supposing G has the set, say 1, 2, 3, right? And you pick alpha in our set. So whenever alpha 1 will give me back alpha, it means that alpha will be in my set G, right? And if alpha 2 will give me back alpha, it means 2 will also be in my stabilizer set, the set of stabilizer. Do you get it? Okay, so that's what we mean by a stabilizer. It's a collection of all G's such that when it acts on an element in the set Holmes, it will give you back that same element. So the collection of those elements in G. Okay. The next definition is what we call the G orbit. Now, the G orbit is basically the set of all elements in the set Holmes that can be gotten by applying elements of G to the element alpha in G. Okay, so every time you pick elements in G and elements in G and it acts on alpha and you get some elements, the elements or results you get are collected and these are called G orbits. So this is how we define it. So it's given as G raised to capital, alpha raised to power capital G, and this is what it does. Everything that G acts on, where G is taken from capital G, small letter G is taken from capital G. So that's the definition of our G orbit. Again, it's just basically collecting elements that G acts on when G acts on alpha, okay? Well, it doesn't fix it, that's what it means now, because when it is fixed, we get the stabilizer, right? Okay, now next is the centralizer. Now, a centralizer basically is more like the normal subgroup. For the normal subgroup, if you remember, we said it basically means, so if we have H to be a subgroup of G, then we say the left coset equals to the right coset, like. But in this case, this is normal subgroup, left coset equals to right coset. But in the case of the centralizer, all the elements of the group G can plate with each other. Okay, look at this now. So the centralizer of A will be denoted this way, and this is definition of it, meaning that any G I pick and it acts on this element A, it will give me back A, any G. So any element in G. So if G were to be the set, say Mn, say Q, these are 3 elements. It means that M inverse AM must give me back A, N inverse AN will give me back A, Q inverse AQ will also give me back A. So when you have this kind of relationship in the set G, in the group G that satisfies this condition, we say we have the centralizer of A in G. Okay, so it's an element A in G such that all elements in G can play with it, as you can see on the screen. Okay, so this is obtained when G acts on itself. So you can tell because the element A is in G, so G is acting on itself by what? Conjugation. So this play I called play is actually what we call conjugation, so that the stabilizer becomes what you have on the screen here, right? Because it's acting on itself. Stabilizer, like we said, is going to be something like this, right? It goes to alpha. But now every time it's giving you back A, right? In this case here, say it here and say it here. So it now can be defined, as you can see on the screen, based on the fact that it satisfies the fixing of the element in G, not a different subgroup. It's G itself, right? So that's the definition of a centralizer of A in G, denoted as you can see right here. Okay. The next definition you need to know is what we call the normalizer. It's similar to the normal subgroup. Okay, so you have H, that's a subgroup of G, and the normalizer is denoted this way. It's different from the normal subgroup, but it's similar in the sense that the definitions are almost the same, but now the element that is picked is from H itself. Remember, A for the centralizer, A was taken from G, right? But now we're going to pick the entire H, a subgroup of G, and allow all elements of G to play or to have a conjugation on it, right? So you have something like this, okay? So that would be like G inverse. So that's what you have on the screen here. Let me clean this. So this is how we write it. Similar. Instead of A, now you can see that the entire subgroup is what you have right here, okay? And we can also write it, as you can see on the screen here, or this way, as I had written earlier. It's almost like normal subgroup, okay? So, but in this case, it is not cosets, right? They are just elements of G acting as conjugation on a subgroup of G, okay? Not an element. For an element of G, and then all elements of G acting by conjugation on that element, we have a centralizer. But an element of G acting on a subgroup of G by conjugation, we have a normalizer, okay? Okay, so let me see. So the stabilizer of the subgroup of H would therefore look like this, right? Because like you know, we said stabilizer, what it does, it takes alpha G and it gives you back alpha, right? But in this case, we have HG giving you back H, right? So they are almost similar. But then we'll define them based on subgroup, define them based on an element. The next is the center of G. So the center of G is denoted thus, okay? It's almost similar to the element, picking an element in G. But instead of picking just A in G, the center does it for any X, all X in G. So for the centralizer, okay, it's just an element. For the center, it is the entire elements, all the elements that can do just that, okay? They can have conjugation as you have acting on them, as you have for a single element when you're looking for the centralizer. Okay, so three main things that are similar but not the same. We had the centralizer for an element A, okay, in G. Then we had the normalizer for a subgroup H. And right here now we have the center of G for all, can you see here? All X, all elements in G, and you can denote it this way, okay? So three definitions, very similar. Carefully note the differences. Next, a finite group G is said to be a P group. So what's a P group? If its order is a power of P, where P is a prime number. So what's a finite group? When is it called a P group? So you know what order is. So if G equals to this element, A, B, C, clearly the order of G will be the number of elements in it, which is 1, 2, 3, right? So we have 3 elements. In this case, is 3 a prime number? Yes, number 3 is a prime number. Therefore, this group that I've written on the board is a P group. Okay? Now, if we reduce the numbers now, or let me increase it to 4, right? Let me increase it to 4. Make it 4. C, D. 2 is also a prime number, so that's a P group too. So the order of G in this case, how many elements? You will say there are 4 of them, right? Okay, but 4 can be written as what? 4 can be written as 2 raised to the power 2. Agree? So is this a P group? Yes, it is a P group because it is a power of P. Do you understand now? So you have a P group. Okay, so G is a P group. So we call it a P group if it's a power of P. Now, let G, the next definition says, let G be a group if T is a subgroup of G and the order of T is of this prime power, P raised to power R, where R is greater than 0, then T is called a P subgroup. So it's similar to the P group, but now this is a P subgroup. It's basically saying the same thing for that the condition we had for a group G, but now we have a subgroup satisfying that. And so if the subgroup satisfies it, we call it a P subgroup. For instance, let's look at the set of integers modulo 2. Clearly this has elements, what? Remainders, right? 0 and 1. So what is the order of this integers modulo 2? Definitely you will say it is 2, right? So this is a P group, right? So we found a P group. So G is a P group in this case. Can we consider the set of integers modulo 4? So this has elements 0, 1, 2, and 3, right? So if I happen to have a subgroup, say H, and my H has elements 0 and 2. Okay, this is my subgroup. Is the subgroup H a P group? Yes, it is. H is clearly a subgroup of the set of integers modulo 4, right? And the order of H is equal to 2. 2 is a prime number, so this is a P group. Okay, so we have seen two definitions added, P group and a P subgroup. The next definition you need to know is what we call a silo P subgroup. Now, if G is finite, because we need to be able to count the number of elements in G, right? If G is finite and the order of G is P raised to power R times M, where R is greater than or equals to 1, and P does not divide M, and H is a subgroup of G such that the order of H is P to the power R, then we say that H is a silo P subgroup. So let's give you an example of what we say here. So if we have the set of integers modulo 5, for instance, what are the elements? 0, 1, 2, 3, 4, right? Those are the elements, right? Because it collects remainders. How many elements? So what's the order? So let's G because these are set. What's the order of G? Clearly the order of G will be 1, 2, 3, 4, 5. So it has 5 elements. If I have a subgroup, say H, I want to use a better example. Let's say I want to make it be represented as P raised to power times M. Let's use integers modulo 6. Okay, so that it'll go all the way to 5. I agree. So that should work. Now we have 6 elements, right? And how do you write 6? 6 is the same thing as 2 times 3, right? Okay, so if we have H and the elements of H again is 0 and 2, right? What then would you write this to be? It means this is P, right? P raised to power 1, and my M will be 3, based on this definition here. PR out of G to be equals to P raised to power RM. So if P is 2 and M, P 2 and M is 1, so I have this. So it means that my order of H, which is 2, is same as 2 raised to power 1, right? Which is same as P raised to power 1. So therefore, in this case, my H can be called a silo P subgroup because it's the whole of this entire 2 raised to power 1. Okay, so we have a silo P subgroup there. Okay. So this has simple examples. We could discuss more in class, and you could ask more questions online, which could make it easier for us as we study the video. Okay, let's continue now. Now that we've gotten all the definitions in place, we now take theorem 3.1.3. I had asked you earlier if you have the hard copy of the lecture note precisely. The video is actually the summarized version or a brief version of the main lecture note. It's broader in the lecture note, so try and get the hard copy of the lecture note. Now, theorem 3.1.3 states that any homomorphism, now you know what a homomorphism is, right? We say if you have theta and it maps G into G prime, and then if you take say A comma B in G, then theta AB will be the same as theta A into theta B, right? That's homomorphism. So let's recall that, because that is key why we're able to use it in all of our proofs. Okay, so any homomorphism rule, so sorry, there's a space here, right, that takes G into the symmetric group on the set Holmes gives rise to an action rule of G on the set Holmes. That's the first statement of the theorem. The second statement, which is what I will need you to know by heart because we'll be using it in another video later, says conversely, let G act on the set Holmes, then to each G in capital G there corresponds a map rho with a subscript G that maps the set Holmes into itself, such that alpha rho G will give you alpha raised to power G, and this is a permutation on the set Holmes. Moreover, the map rho, which maps G into the symmetric group on Holmes, defined by this, is a homomorphism. Accordingly, we can say the map rho is taken from the set of, or the collection of all homomorphisms of G and the symmetric group on the set Holmes. Okay, so this is a statement of a theorem. So the first one simply is basically saying, so which is what I'm going to be proving. The first one, the second one I'll need you to know by heart. Okay, so this first one basically is saying that if I have this kind of map and it is a homomorphism, then I will get a group action. That's what it's saying. So what is a group action again? Let's go back to the first definition of a group action. Now, a group action is a map, right? A function from the set, a group action which maps the direct product into the set and it satisfies these two conditions, right? So now, and the group action for us, we already even know it's a homomorphism, so that helps us. So let's go back to what we intend to do. So I said we're going to show the proof of this right now. So now we're here with, on the screen is a proof of that particular statement, the first statement of theorem 3.13. So it says, we want to show that we have a group action. So this is the map, right? So we're going to move with that. So given a homomorphism, so we have this homomorphism, right? So we define the map. We already know that it's a homomorphism and it's taking G into the symmetric group. Now, if that happens, if you remember what we talked about when we were defining, I want to go to that definition. Yes, when we're defining the permutation representation, so we're going to be using the permutation representation because actually that map is a permutation representation. You can see here. So we just need to work with this definition and use what it does. This is what it does. Okay, it takes alpha rho G and it takes it to alpha raised to power G. So we need to remember this representation. This is what we're using in the proof. Okay, so let's go forward now. So we took it, we defined it because we know what we're mapping from. We're mapping from G into the symmetric group on the set Holmes. So it will satisfy these conditions as you can see on the screen. I'm able to write this because of the definition of a group action. We're picking two elements in this, right? The two tuple, and it's going to go into the set Holmes, right? But we know that this is a permutation representation, right? So it will look like this, okay? For all alpha in the set Holmes and for all G in the group G. So we seek to find out if this our mu will satisfy these two identities, right? So how would that look like? So we'll check the first one now. So alpha G all raised to power H, what would it look like? We know that alpha G by the definition over here, so we're going to use this because this is easier to work with, is going to be this here, Now, if H acts on it, if you then pick it with H, the H will be by the side, like here, simply following the definition of the map. Okay, but we know that rho is a what? A homomorphism. See it here. So because it's a homomorphism, this thing is split in two. What does it do? Homomorphism, what does it do? It brings them together. So that's why we have them together, as you can see here. So we had G rho and H rho. Rho is a homomorphism, so this will be the same as GH with rho at the side. Okay, so that's how we got this side here. Okay, so let me clean this. So if that happens, what is this by definition when rho acts on it? Look at what happens here. When we have alpha G, is same as alpha G rho. You can see? So because of the permutation, this becomes this right in here, right? So now we have, I'm going to write this other side. We have GH and rho here. So what would that look like on this side? There's alpha, there's alpha, there's alpha, so there's definitely going to be alpha here. And this is this here. So instead of G, we have GH. So definitely I'm going to be writing GH up here. So that's how we got this value here, simply following the definition. So you just compare the definitions and get your output. Okay. Okay, so we finished the first identity. We need to prove the second identity. For the second identity, it says we should look for alpha 1 equal to alpha raised to power 1 equal to alpha. So now alpha raised to power 1, by definition, if we have alpha G, it is same as alpha G rho, right? So now what will alpha 1 be? So alpha 1 would definitely be something like this. Wherever there is G, I put 1. And we have rho. Okay, so alpha G rho is this. But we have shown that 1 theta in class, do you remember? It's equal to 1, right? Because theta was a homomorphism in class. And this is also a homomorphism, right? And this is 1. So this thing here, sorry. So 1 rho in here, meaning that 1 rho will be equal to 1. So that's how we got here. That's the sense you see there. And so what is 1 times, so wherever I see, so this alpha 1 will be equal to alpha times 1. What is alpha times 1? It's simply alpha. And that is all to the proof. So the conclusion, which I don't have here, I have not stated it there, we're supposed to conclude. So what do we conclude? We then say, since rho satisfies, so you need to conclude the identities one and 2. What does it follow? It follows that G, okay, it follows that any homomorphism rho G gives rise to an action rho of G on the set homes as required. So that's the conclusion of the theorem. Okay, so again, feel free to go through the video slowly. I know there's a way you can make me talk slower. It's possible I was fast. I apologize for that. And go through the slides and the video again. In class, I'll go over the videos as we've been doing for the past few weeks now. And please feel free to ask questions on the video on each of the topics and anything you need clarity for. Okay, so the next is just theorems I need you to know by heart. The first theorem, that this is called the fundamental counting lemma. This one here. Another name for it is actually the orbit. Another name for it is the orbit formula. Okay, so now The fundamental counting lemma states that let G act on the set homes, where G and the set homes are finite, so meaning you can count them. Then once you have told to state the fundamental counting lemma or the orbit formula, just say it is a formula that satisfies this, or it says let G act on the set homes where G and the set homes are finite, because we need a group action for this to happen, right? Then the order of G is equals to the order of the stabilizer times the order of the orbit. Okay, so now the next thing I need you to be able to state is what we call the Seiler's theorem. Now the Seiler's theorem, this describes the existence, conjugacy, and number of Silo P subgroups within a finite group. So now we have a finite group, and this helps us to find this number of Silo P subgroups, the number of P subgroups, what can happen within the group, okay? And if possibility of conjugacy, okay? So what are the identities that Seiler's terms satisfies? It satisfies the following. It says Seiler's theorem states that let G be a finite group. So if you have a finite group G, then these conditions must hold in that finite group G. Come what may. That there is at least one Silo P subgroup H of G, as you saw when we chose G to be the set of integers modulo 6, there was one, right? So the second is, if Y is a P subgroup of G, then Y satisfies this condition here for all X and G. Okay. The third is, if H1 is any Silo P subgroup of G, so you can find any Silo P subgroup of G, then H1 satisfies the condition for some G, for some element G in capital G. Okay. And the fourth one is that if N is the number of Silo P subgroups of G, so you found all the Silo P subgroups in G, then the number of Silo P subgroups, that's NP, sorry, there's a P right here, not just N. There's a P at the base of the N. Then the number of Silo P subgroup divides M, where M does not divide M, and NP is congruent to 1 modulo P. Remember what M is. M is the order of you remember when we said G was equals to P raised by Rm. So that's an incomplete statement there. So that's what M is, okay? So P does not divide M. And the number of Silo P subgroups is always congruent to 1 modulo P. So I need you to know this. I need you to know these theorems by heart. It's possible I prove them in class. So for further understanding and assimilation. Okay, so these are references if you need more insight into what want to do more research, and if I ask you to do more research, these are materials you can go through to dig deeper. Okay, thank you.